Okay, lesson 2 is slope fields. And as I said, we introduced them a little bit on Friday, or Thursday into Friday, I guess. Slope vector or direction fields are graphical representations of differential equations. You can use slope fields to visualize the parallel curves that solve the family of solutions to a first-order differential equation without algebra. For example, the equation dy dx equals y has the property that the slope at any point is equal to the y-coordinate at that point. And this graph at the right shows that. We can draw many line segments at each marked point showing the slope of the curve there. Now, the idea here is that, so dy dx, of course, we know that as another way of talking about slope, right? So they're saying that in this slope field, the slope at any point is going to be equal to whatever the y value is. So if I look, for instance, here when y equals 1, notice all those slopes are drawn in a positive sense, kind of indicating the angle of what you would think of 1. So like when we think slope of 1, that's rise 1, run 1, right? If you go up another row, oh wait, that's not at 1, is it? I forgot they count. In my brain, sorry, I'm thinking this is 1, 2, 3, 4, because that's what's logical. If I had made the notes, that's what it would be at least. But, okay, so realize the one that's closer to 1 is right there. That's more a slope of probably, what, 1/2? You've got 1, you've got, but each time, what's happening to these little lines? They're getting steeper, aren't they? Because as the slope is going up, it's getting steeper. Down here, what do you know about the bottom half of the graph? These are all slopes that are angled negatively, right? And that's because the y value down there is negative. If we were to draw what this graph would look like, you can kind of follow, there's curves you can kind of follow there, right? And remember, this represents family of curves. So as we look at this, anytime think about the plus c values, right? There's always all these plus c values, so there's always all the different options. Okay? Now, we are going to start talking about, this is slope field. You can draw any one you want. You can get a general solution. But in order to get a particular solution, we talked about this last week, you're going to have a initial condition, right? In order to work out that grape juice problem, you had to have an initial condition. So we will talk about that as we go along today too. Okay, let's go into example 1 and try and make it all make sense. So sketch the slope field for dy dx equals 3x minus 2 using the table below. Now, notice, what do we have, 5? Okay. Which I guess technically we have 5 is enough, but sometimes they give you charts and really you could fill in this whole chart because in a way, if you think about it, there's what? There's 25 places we're going to fill in slope. Okay, in other words, if we're filling in slope, the slope at each ordered pair, so at -2, 2, -1, 2, 0, 2, do we need to fill in slope on the axes as well? There's technically 25 places that we're going to fill in slope. Now, here's the deal. There's going to be some overlap. Okay, each problem is going to vary, of course, but there's going to be some overlap. Remember I mentioned dy dx is your m. In this particular problem, what's the only variable that matters? It only matters what your x value is. Okay, y values aren't going to affect the slope of this problem. Okay, we'll get to the next one where we will. But the idea is the x value will determine the slope of the problem. What are the x values presented on this graph? I think we just have the basics, right? -2, -1, 0, 1, 2. So I'm just going to fill in my chart with the x values. And in this case, because it's only 3x minus 2, because there's no y in the problem, we only need x values. And as I said, that's because it's 3x minus 2. If we need, you know, if there was 3x minus 2y, we'd have to have xy pairs and talk about each pair. So, what happens when you put in negative 2 to this equation? 3 times negative 2 is negative 6, minus 2 is negative 8. So, now we can go in and fill in the whole curve, or we can do this bit by bit, but okay. Where does x equal negative 2? Here's the x-axis. Here's negative 2, yes. X equals negative 2 at the ordered pair negative 2, 0, negative 2, 1, negative 2, 2. Are you thinking about this with me? Negative 2, negative 1, negative 2, negative 2. So on the graph, where your ordered pairs are going to have negative 2 as the x value. And that's all of these right here, yes? What's the slope at all of those pairs going to be? Negative 8. Now, so when you draw this, negative 8 is, in my brain, a very steep slope, yes? And it also has to go in a negative direction, which means it's angling left a little bit, or I don't, you know, down and right, up and left. You have a negative slope view in your mind, right? So what I'm going to do right now is I'm going to put little marks of these, and they're going to be very steep. But slightly angled to the left. Now we're going to repeat this process with negative 1. If you put in negative 1 to the equation, 3 times negative 1 is negative 3, minus 2 is negative 5. So this is very tedious, because what's the slope of negative 5 look like in comparison to negative 8? Still pretty steep, still negative, but a little less steep, right? And I guess if you want comparison, you want maybe it'd be easier if we go ahead and fill out the rest of the chart. Maybe I should do that. So what about anytime x is 0, what's my slope going to be? Okay, so we're going to have to do negative 2 slopes. Anytime x is 1, the slope is 1. And anytime x is 2, the slope is going to be 10? Really? No. Huh. How did I?
Where'd the 10 come from?
I don't know. I got nothing here. Okay, so for a little bit of comparison, those are the different slopes we're going to have to represent. Okay, so the slope of negative 5 here. Anytime x is negative 1, my slope's going to be negative 5. So still a negative slope, but my attempt, I don't know that it's the best attempt because some of them ended up looking about the same, I feel like. But the attempt is it's a little less vertical. Okay. What about when x is 0? What kind of slope do we have? Negative 2. So this is getting slope closer to a traditional, like negative 1 is what would be that middle diagonal, right? So negative 2 is getting closer to that. Okay. But all of a sudden happens at 1. We have slopes that are positive ones, right? Anytime x is 1, my slopes are positive ones. So we're going the other way. It looks something like that. And then when x is 2, my slopes are positive and a little bit steeper because we are at 4. A very tedious task, as I said, because I sometimes look at that, I don't think my slopes look all that different. I tried, I promise. Okay. Now, obviously you can tell the difference between negative and positive slopes, right? There's definitely a difference there. Now, thoughts? Can you visualize what this curve might look like? Okay, some kind of curve. Okay, here's another thought. If you took the integral, you integrated 3x minus 2, what kind of power are we going to go to?
Square.
X squared. What's an x squared look like? Parabola. Thank you for the sound effect. Okay. So you see where this is all connecting here. And that's, and this is something where we don't have to, but if I move my x over, and this is dy equals 3x minus 2 dx, and I integrate that, okay, you can't always do this, I will say. It depends on the difficulty level of the problem. But if I integrate that, this becomes y equals, add 1 to the power, divide by the new power, so 3/2 x squared minus 2x plus c. A parabola, yes?
So what's the point of this?
Well, right now, we're looking at the family of curves. Look, it goes along with solving the integral curve. Just solve me a family of integrals. Okay. It's our graphical representation right now, and we'll do some different things with it. I'm trying to think where all it comes up, and we'll talk about some of them today. Right now, it's just in my opinion, right now, it's just trying to understand what some of these integrals look like what they represent, what the graphical representation is there. Let's see, I think in mine, let's see. Okay, and I'm not saying you have to trace it, but like if I draw that, could that possibly represent a parabola that's part of this family of curves, right? And I'm not the greatest at these, but you can kind of see how there's some curvature there, right? That is the idea of what those look like. So I know the comment I have written in my notes is that the slope field represents the family of curves. And in this case, our family of curves are parabolas. So it's nice when you have something like that you can kind of see what the integral, oh, I know when I integrate 3x minus 2, I'm going to get a parabola curve. Okay, and these are just general solutions, right? Because I don't have an initial value of this. It's okay. Now, one of the things we'll do is, okay, draw me the curve that goes through 1, negative 1. Well, then you'd be looking for the curve that specifically goes through that initial condition. Okay? Okay. Now, example 1 kind of let us start off a little easy. There was only an x value in here, right? Notice when there's only an x value, all my columns where the x values were consistent had the same slopes, yes? Up here, this visual up here, all the y values were the same because this one only had a y in it. There was no x. So then the horizontals were the same. Well, guess what? Now we get x and y. Now, first thing I'm going to suggest is that we get this in a more workable format. Solve for dy dx. Because I need to plug in values and see what the slope looks like at different points, and I don't want to do that here. So if I keep, let's see. Oh, wait, no, well. I was going to keep the negative y dy dx where it is, subtracting 2x over to the other side. Not sure why I did that, but. And then if I divide by negative y, negative divided by negative is a positive. So I'm going to say that my differential equation this time is best represented as dy dx equals 2x over y. Okay. Now, this is a situation where there's a lot of different xy commas we could put in our chart. I'll probably end up expanding my chart a little bit more than that, just because, I don't know. And some of it we can do in our head and not necessarily talk about. But let's see, where do I want to start? Let's just start with negative 2. If we start with negative 2, and I'm actually going to say, okay, negative 2, what's that first point up there? Negative 2. Well, where are we plugging those values into? 2x over y. So if you do 2x over y, 2 times negative 2 divided by negative 2 is going to be what? 2. So my slope at that point will be 2. If I put in negative 2, negative 1.
How do we get from negative?
So I'm just picking ordered pairs here.
Oh, you're picking that.
Yes, so I just the first ordered pair I picked was right here. Now I'm just trying to get us something to get us started. Well, how about I start down at the bottom and work my way up? I don't know. Yeah, I agree. Are we okay? So I guess that's this point down here.
So are you supposed to do that for all the x values? Is that chart's not big enough?
I know, exactly. And this is where, okay, so as we're going to do the first set, and there's some things we'll discover where there'll be certain values we won't really have to proceed with anymore because of certain things that happen, if that makes sense. I know that's kind of vague in a way, but give it a chance, okay? Now, I will say that I know I did write some other pairs, and I kind of doubled up. So, yeah, if you can write small enough and you want to double up or something, I mean, technically, could you do this for every single point on here? You could. But what ends up happening is you end up doing some of it in your head. You end up realizing some patterns, those type of things, okay? Okay, so I guess we're starting at the bottom because your teacher has issues. Okay. What about negative 2, negative 1? Negative 4 divided by negative 1 is going to be positive 4, if I'm correct. Don't let me make mistakes, please. If I put in the ordered pair negative 2, 0. What about the ordered pair negative 2, 0? Undefined. Is there a generalization I can make there? Huh? Okay, possible asymptote, but
Everything divided by 0 will be.
yeah, one of the generalizations right here is anytime y is 0, my slope is going to be undefined, if you will, right? So do I need to try negative 1, 0, 0, 0, 1, 0, and 2, 0? No. Okay. Negative 2, what do I still need to do? Positive 1. So what's negative 2, positive 1? It's going to be negative 4, right? And if I do negative 2, positive 2, negative 2. Are you noticing connections there between the negative y values and the positive y values? It just flipped my slopes, didn't it? Same slopes, but different numbers. Now, you can go ahead and put in some of these slopes if you want. I mean, we work a lot with slopes of like 2, 4, and 1 today are the numbers that I see on my stuff. So you want to go, so at negative 2, so down here, because I'm going down, we're going to have a slope of positive 2, which means something like that, right? Maybe a little steeper, I don't know. At negative 2, negative 1, I'm going to have a slope of 4, so that's steeper. Slope of undefined, don't write anything in. Okay, general rule of thumb is slope of undefined. I mean, a lot of times we use that for that's a vertical line when we talk about slopes back in algebra. But don't write anything in, just leave those spots blank, okay? And so then when you get up here, well, negative 2, 1 is going to reverse, and we're going to have the negative 4 slope. And then up at negative 2, 2, you have the negative 2 slope there. Okay. If you wanted, what's another generalization we could go ahead and hit on? We looked at 0 in the denominator. What happens when you have 0 in the numerator? I just picked 0, 2. But what's going to happen when you have 0 in the x value? You're always going to have a slope of 0 there, aren't you? Do we need to fill in a bunch more ordered pairs there? No. Now, what's the slope of 0 look like? Horizontal line, yes. And maybe I shouldn't have jumped. Maybe we should have done our, negative 1s here. But so at 0, 1, 0, 2, 0, negative 1, and 0, negative 2, we have 0 slopes. Now notice, I didn't put anything at 0, 0, did I? And then because 0, 0 is just, it's a mess. It's an undefined slope and a 0 slope. Just don't put anything. Okay, that undefined kind of pulls rank, if you will. Now, should we look at what happens maybe when x is negative 1? Because if you're seeing the connection, there's going to be a connection between the left half of the graph and the right half of the graph. Just like there's kind of a connection between top half and upper half, yes? And in all honesty, as you see connections, feel free to take off on your own and, there's no right or wrong way of what order we do this in. Okay? So if I go here and I'll do negative 1, negative 2, negative 1, negative 1, and I'll do the positives then. So negative 1, negative 2, negative 1, negative 1, negative 1, positive 1. Whoops. Negative 1, positive 2. Notice I skipped zeros, right? Zeros are done. Don't need to think about them. So when I put in negative 1, negative 2, positive 1, negative 1, negative 1, positive 2, negative 1, positive 1. It's negative 2. Negative 1, positive 2. It's negative 1. Again, is there that negative relationship between upper half and top half, or bottom half? Okay. So fill those in however you want there. So the negative 1, 2. Here's my negative 1 slope. Negative 1, negative 1. There's a negative 2 slope. Oops. Gosh darn it. Then down here, we're reversing it. Now, you can continue making numbers on your chart, or you can also kind of start generalizing. Okay? What's going to happen when I get up here in quadrant 1?
I'm gonna flip what's on.
Going to flip which ones? Take quadrant 2, and these were negative slopes. Over here is going to be the positive versions of them, right? Okay, same thing down here, yes? Now, and here's the deal. I mean, quadrant 1, you're plugging in, if you plug in 1, 1, if you just need a test value, plug in 1, 1. Oh, 2 over 1, that's 2. So I'm going to have a slope of 2. As I said, this is where you can do this in your head just as well. If I plug in 1, 2, it's 2 over 2, that's a slope of 1. If I plug in 2, 1, now we're back to that slope of 4 from earlier. And this is our slope of 2 up here, right? Yeah. It's a very tricky game, isn't it? Okay. Same thing down the bottom. Here we're going to have the negative versions. So get your negative versions filled in. Let's see. The 1, negative 1 is going to be, what are we looking at now? Negative 2? Yes. This is my negative 1. No, I reversed. No, I got that. Then when I put in 2, negative 1, there's my negative 4. And then 2, negative 2, there's that negative 2 again. Now, let's see. What did the directions say? Sketch the slope field. Done. Can you maybe start to visualize where the curves would go?
Is
I mean-
it like this? Or is it like this?
You do have a lot of things right here.
I'm going to go with,
It's like sideways for apple. That's what I was.
okay, now, keep in mind, we have zero slopes here, yes? Undefined here, right? So think more along the idea, nothing's going to be on that, touching that.
I'm so confused.
Okay? I say, and I'm just realizing I don't even have anything drawn in there.
Goofy hourglass.
No, because we're not going to go through here.
Well, no, but it's that's why I said goofy. It's in two parts.
Oh, okay.
Like, bro,
Oh, I see what you're saying.
so
Okay,
it's not
okay.
gonna work ever.
Okay. So,
I say never.
and officially, this says sketch the slope field. This is sketching a slope field. They didn't tell us to draw any curves in, so we don't have to draw any curves in. Okay? They might give you information to do that. They might not. It does say then use integration to solve for the general solution. So if we take this and solve for the general solution, think integration by separation, yes? Because I don't know how to integrate 2x over y. Yuck. But what can I do? Y is on one side, x is on the other side, yes? So if can I do this all at one step? If I multiply y to the left, I'm going to have y dy. If I multiply dx to the right, I'm going to have 2x dx, yes? Works out nicely. And then if we integrate both sides, we end up with what? 1/2 y squared equals x squared plus c. So you've got, and you could, depending on your situation, if you solve this, let's see, I am going to multiply my 2 over, so it's y squared equals 2x squared plus c. And then and I guess here's the deal is, notice, gosh, how much pre-calc and trig do you remember? If I would have solved this and gone y squared minus x squared, go back to conic sections chapter from January of last year, exactly. Y squared minus x squared is a hyperbola, which is the two curves that could either go like this or like this, or our reciprocal function is the one at an angle, right? Okay. So, I mean, that to me kind of says what it is. Because y squared is the first variable, again, don't know how much you remember this. When it was y squared, if it was x squared minus y squared, it went like this. Because it's going to be y squared minus x squared, it would go like that. It would be the vertical one. Okay. If you solve it this way and make it y equals, it's y equals plus or minus square root of 2x squared plus c, which that doesn't do quite as much for me in terms of, you know, the other one figured it out a little bit for me. So I will say, oh, actually, I take that, well, yeah, if I make this, I'm going to go back to this one. I like it better. Y squared minus 2x squared equals c. These are all options. The directions were vague. It just said solve. It didn't give us a certain form to leave it in. And that's, you know, it's one of those things you kind of be familiar with all of them. Okay. With slope fields, always the tendency you're going to see, there's going to be patterns to look for. Everyone's a little bit different, but you've got to look for patterns and kind of generalize. Or you can do every single ordered pair, right? So they're a little tedious. They take me a little while to do slope charts, or slope fields. Take me a little while to teach them, thus, for the same reason. Okay, example 3. Consider the following equation. dy dx equals negative x over y. Compute dy dx at each set of points, and then answer the following questions. And because I was trying to get a lot of this on the same page, I did not zoom in. but I think we'll be okay. So we're plugging into negative x over y. What do we know about it? The ordered pair of 1, 1? We're going to get negative 1. At negative 1, we're going to get positive 1. At negative 1, negative 1. And at 1, negative 1. 1. Plugging those values in, right? dy dx is positive in quadrants blank and negative in quadrants blank. Did you figure out what order they went in? 1, 1 is in quadrant 1. Negative 1, 1 goes left 1, up 1, so there's quadrant 2. Negative 1, then is quadrant 3. And 1, negative 1 is quadrant 4, if you will. So it's positive in quadrants 2 and 4. Negative in quadrants 1 and 3. Okay. Same thing. Still working with the same dy dx all the way through this entire page. Now what about, which keep in mind it is negative x over y, right? Okay, what's happening at 1, 0? What's happening at all of these? They're all divided by 0, aren't they? So all of these undefined. Okay. Write an equation that would describe the slope as undefined, and write an equation that would describe the slope as 0. What kind of line has an undefined slope? Okay, but what line? That's what the slope is, but when we first learned slopes, the vertical lines were undefined. Exactly, one of those two, right? The vertical lines were undefined. How do you write the equation for a vertical line?
X.
It's x equals a number, correct? So I'm just going to actually use x equals a, meaning x and a is some number. And this represents any vertical line. What about the slope is 0? That's your horizontal, and that is y equals a. And that is any horizontal line. Okay? Consider another set of values. Again, all the way down the page, dy dx is negative x over y. What do we got? 1 over 1 is going to be, or negative of 1 over 1 is going to be negative 1. What about 2 over 2? Or 2 comma 2? Negative 1. The ordered pair negative 1, negative 1. And negative 1. Okay. What equation would express dy dx equals negative 1? In other words, if we integrate this, essentially. Okay. If you if we integrate this, or if you think about what would you take the derivative of, dy dx, if we integrate it, goes up and becomes y. What's the integral of negative 1? Negative x. What about if it's dy dx equals 1? Then you would have y equals x. Okay. And there's a reason for thinking about that, because as we go to fill out our slope field, y equals x is a line, yes? Y equals x is that perfect diagonal line. And what is the slope going to be anytime on the y equals x? Well, so these points are on y equals x, right? 1, 1, 2, 2, you're always going to have a slope of -1 on there. What about if you're over here on this diagonal one? Then your slope's going to be becoming the +1 there, okay? Now, this is a horrible place to run out of time. In terms of if the big Q erases overnight, I'm not going to have this information. But it's all right. It might be a good idea for me to enlarge this tomorrow anyway. So tomorrow we will, or you can even start doing it, but we will go through and work on drawing a slope field, okay? They're trying to give you some things to think about, some patterns to look at, so you don't just have to find every single ordered pair. And then we're going to attempt to draw the particular solution that passes through the point 0, 2, and based on what we decide it to be once we draw it, write an equation. Okay?
Sounds fun.
So, then let's see. We have a couple questions to ask about it. We have some matching section. We have another slope field on the next page to talk about. So, okay? Okay, we'll talk tomorrow.